So welcome to the revision video for iGCSE Physics. This is just one whole topic. There are some more videos which are individual subsections, but this is for if you finish the entire topic. So there are 8 videos in the series. If you like and enjoy, please subscribe. Okay, so this is another iGCSE intro topic, 6B, magnetism. So we're looking at magnetic behavior as part of this. So magnets repel and attract each other, magnets, and attract magnetic substances. So you can see north and north will repel and north and south attract. You should be able to draw a field pattern. So you've got a region of space where the field acts. So you show the direction that an object would move or the force lines. They shouldn't ever join. You should have an arrow on. The more that there are in a space, the stronger the field. So there it's very strong. Here it's quite weak. You should be able to show a north and south and a north and north. And the easy way to remember it is, where do birds fly in the winter? Well, they go south, north to south. So from England, they go to Africa where it's warmer. So the direction must be north to south. Often we have red for north and grey or blue for south, but that's not always the case. Induced magnetism, so if I place a material in a magnetic field like an iron nail, it will itself become a magnet and then attract to other nails. So that's called magnetic induction. Here we've got a uniform magnetic field, so you've got a region of space where the lines are straight. They might curve at the edge, and the more lines there are, the stronger the field is. Charged particles, so particles of alpha, beta, gamma move through a magnetic field shown by the crosses, and they might curve or go in a straight line. So if they are charged particles, they tend to curve one way or the other, and depending on their charge to mass ratio, they will curve more or less. So you can tell whether it's alpha, beta, or gamma, which goes straight on. You should know with the field lines that these are crosses. So it's thinking like Robin Hood with arrows. So if Robin Hood is shooting an arrow, the arrow is going away from him. So it's an X, showing that the field goes into the page. If it was a dot and a circle, it will come out of the page, and that would show that the magnetic field is going in the other direction. Now, we've also got Fleming's left-hand rule that applies for that, and you can see Fleming's left-hand rule. So direction of force is the thumb, first finger of the magnetic field. Direction of current is the second finger. Also, I quite like to use the term FBI. So F is force, B is the magnetic field density, and I is the current. Much easier to remember, but it's up to you how you do it. Units-wise, I like to talk about the magnetic flux density measured in Tesla. iGCSE tend to shy away from talking about it quite in that term. They talk about magnetic fields, but actually the flux is good because it's a symbol B measured in Tesla, and it's actually defined as the number of flux lines or lines that pass through. You can see these magnetic field lines through a certain point on a surface. That tells you how strong it is. More lines, stronger. So like we said on this diagram, if there were more lines, it would be a stronger field because there's more lines of flux. Ampere, that's what we've done before. So 1 ampere is 1 coulomb per second. So it's electrical current, the flow of 1 coulomb of charges per second past a point. Newton is equal to the force that would give a mass of 1 kilogram, an acceleration of 1 meter per second. It's a vector quantity. We use the formula F equals ma, or F over m is a. 1 Newton is 1 kilogram meter per second squared, or slash second squared. So there you go. That's the introduction to magnetism 6B. So this is the iGCSE topic introduction to magnetic effects. So what have we got? Well, we've got the right hand grip rule for magnetic behavior. So there's your right hand, has to be right hand. Electric current in a conductor produces a field. So when electrons flow in a wire, we create a circular magnetic field that will make a plotting compass turn in a circular direction as you move it round. You think, okay, big wow, what does that do? Well, what we can do is if we take lots and lots of loops of wire or turns, we can add up all the right-hand grip rules on one side and on the other side. So remember the wire on this side comes out the page and it goes into the page and out the page and into the page. So because you're turning your thumb, thumbs up, thumbs down, thumbs up, thumbs down, all of those field lines reinforce to create what looks like a bar magnet. And we call this a solenoid. Now then what we can do is make that into an electromagnet. So an electromagnet is made from an iron core typically, or a nail. We do lots of turns of insulated wire around the core, And the current then flows around the wire, not in the nail at all, just around the wire, because remember we said it's insulated. That induces a magnetic field in the core, and that can be used to create moving parts in a system. So it could be, for example, here we have an electromagnet, and this is a funny one. It's basically like a U shape, but it's still an electromagnet. It's just been basically made into a horseshoe shape. When I turn the battery on, the north and the south both attract the ion contact. It breaks the circuit, and the hammer moves gong, and then it comes back again. Because the circuit's broken, the current turns off, the electromagnet's gone off, because we can make it turn on, off, on, off. And so we've got effectively an electromagnetic effect. We can do things like the motor effect, where that's current passes through the wire, and the wire then experiences a force due to Fleming's left-hand rule we talked about. So force, F, B, magnetic field, I, current, or direction of force, magnetic field, direction of current. If a wire has a current flowing through it, and it's in a region of space where there's a magnetic field, it will get pushed out. And the force is up if the current flows that way. But if the current flowed the other way, the force would be down. So you can make children's toys, electromotors, that kind of thing. And you can make a loudspeaker. So this is a little bit complex. So magnet, bit of a weird one, because it's like a bit of a bucket. And then the middle of it, because remember this is a slice, a flat slice of it. So it's like circular, but in the middle is the south, on the outside is the north. So what happens is we coil some wire around a cone, and when you get an alternating current in the coil, it pushes and pulls the paper cone backwards and forwards, which pushes and pulls the air molecules backwards and forwards, which creates a sound wave. We can also, of course, have motors. So electric motor here, we've got carbon brushes, a split ring commutator. So there's a split, which means that as it spins, as we get a push, it doesn't tangle up the wires, and these little carbon brushes will wear away over time and can be replaced. In a car, you would see that, some of these old-fashioned devices. And the clever bit with this is, although the field is that way, because the coil of wire, the current flows up one way and down the other, due to Fleming's left-hand rule, the force reverses. So force up, current towards us, current away from us, and force down. So there you go. That is electromagnetic effects. Okay, so this is an introduction into iGCSE Physics with Induction, section 6D. So voltage is induced in a conductor or coil when it moves through a magnetic field, or when a magnetic field changes through it. So there we've got my magnet. I push it into the coil or loop of wire, and the galvanometer, which is like a sensitive ammeter, will show a potential difference or a current moving through the loop. Now, of course, if I pull the magnet the other way, it's going to reverse. Or if I push it in and then I move the south to the other side and pull the south out, then the needle reverses. So that is induction. Now, transformers is all about changing the size of an alternating voltage by having a number of turns on the input and output side. So here we've got a transformer core that looks a bit like a donut, and we've got a primary coil. So this is a coil insulated wire, and across it, we have an alternating current and an alternating potential difference. So constantly, this is alternating just like the trace at the bottom here. Well, if that happens, what would I create? Well, I induce a magnetic flux that works around the transformer core one way and then back, and one way and back. So they don't create power, but what it does is it passes through a current. So we have a current here, and we have a magnetic field, and this induces or creates a alternating potential difference in a secondary core. Now the clever bit is we can change the number of turns, and due to the right-hand grip rule, here we'd have lots of turns, here we have less turns, so I have a high potential difference, and this steps down the potential difference to a lower potential difference, but it increases the current because the power should equal the power that goes in. So power input should equal power output, which is one of our formulas. And you can see here the other key part of the maths is potential difference on the primary, potential difference on the secondary, and the number of turns on the primary and the number of turns on the secondary. So I find the ratio you can either do of primary to secondary with potential differences, or you can do primary on one side, secondary on the other, like this one is. So the voltage, potential difference on the primary divided by the number of turns will give you the voltage on the secondary divided by the number of turns on the secondary. So what happens is I can transform my energy, and by transforming it in something called the national grid. So there's a power station, we transform it, we step up the potential difference, then we step it down when it comes to our homes. By stepping it up, we find that we can reduce the power loss. Now, typically, if it was a perfect situation, input power equals output power, voltage on the primary times current on the primary equals voltage on the secondary times current on the secondary. But we often find that transformers are not 100% perfect, and you could work out, if you know the resistance and stuff in the wires, the power loss, which comes out at I squared R. So if I reduce the current quite a lot, I reduce the power loss, and this is why they step up the current to go down the transformer lines, and then they step it down again later. Transformers are made out of soft iron, a soft magnetic material, so it can easily magnetize and demagnetize. That helps keeps it cool and lowers wasted energy. We would never use steel because steel is hard to magnetize. So we don't want a permanent magnet, we want something that can be magnetized and demagnetized. Other part of this topic is generators. So the generation of electricity is by rotation of a magnet within a coil of wire and of a coil of wire within a magnetic field. And we've got to describe the factors which affect the size of the induced voltage. And we've got to use Fleming's right-hand rule. So you can see we've moved to a different hand now, because what we're doing is we've got motion, we've got a field, and we're creating a current. You can see a typical setup here for a generator with slit rings connected. And effectively, when the coil of wire is turned within the magnetic field, we're making a continuous contact between the slit rings, and we produce an AC, an alternating trace. And this is why we use transformers to adapt the current flow, because it's an AC trace. They've got to be an AC input for it to happen. It doesn't work with DC. And bearing in mind as well, one thing to mention is the frequency usually of mains is 50 hertz. Just a reminder, going back to year 9 common. So there you go. That's 60 induction.